Hi, everyone. We're very excited to be here today and to talk to you about unlocking genomic workloads on the cloud. Part of why we decided to have this talk is that the life sciences industry is actually undergoing a monumental shift in the way it works. And cloud is actually becoming central in the way they work and conduct research. This talk is specifically focused around genomics and how technology is completely changing fields like diagnostics and the development of new treatments with the use of data. We'll start by providing an overview of the landscape today and where we are. Then we're going to be talking about some of the challenges with genomics, and we're going to be talking about how cloud can help solve these challenges. And then we're going to be going through some tooling and how to actually use some of this genomic specific tooling on GCP. And finally, we're going to be showcasing a demo of how to do that. So my name is Hussein Al Muscati. I work as a customer engineer in Google Cloud, primarily focused on public sector and life sciences.
And my name is Hatem Nawar. I also work as a customer engineer in Google Cloud focused on life sciences.
We are both based in London and are presenting to you today from our humble homes. As customer engineers, we work very closely with our customers to help enable them to adopt and use cloud and to help them develop solutions that are cloud based. And our primary focus is working with public institutions and research organizations. So to kick off, there's an interesting statement that says there'll be 163 zettabytes of data by 2025. I'll give you a few seconds for you to actually absorb that. So, to give you some context, that is equivalent to watching a cat video that is about twice as long as the universe is old. And to give you another way of looking at it, all the data that has been generated by mankind up to the 1980s is less than a zettabyte. So that means the majority of this data is actually net new. So where's all this data coming from? Well, I mean, part of it is from you taking pictures, uploading them, videos, etc. But a big part of it is actually from healthcare and life sciences. Medical imaging is actually number one, but genomics is not that far from it. And the amount of genomics data is actually exponentially growing and resulting in a huge challenge in terms of how we can handle it and manage this data. This growth means that there needs to be like a new medium or way of handling it. And what is the end result of this? Well, we're already seeing a profound impact on healthcare. We've barely scratched the surface of what genomic research can actually yield, but it's already having a significant impact. In 2018, around one third of new FDA approved drugs actually relied on genomics. And interesting enough, in 2005, Francis Collins, the director of the National Human Genome Research Institute, predicted that most drugs by 2020 would be derived or used using the understanding of the human genome. And we're actually not that far from it. And another interesting fact is by this year, the expectation in 2020, the expectation that there'll be around 26 million people who have shared their DNA with one of the four leading commercial ancestry forms. So this is actually becoming a trend. Another interesting trend is what we call as the rise of genomic biobanks. It's quite interesting. Biobanking is sort of the result of advances in human genome, in computing, and bioinformatics. And if you think of it, it's really a modern way of storing, managing, and analyzing massive amounts of biological data. Many population based biobanks have been formed in different countries, and it's actually becoming a central national strategy. Some examples include the UK Biobank, the FinGen project in Finland, and the Biobank GRAS in Austria. And biobanking is actually quite important because they act as a central hub for other organizations, such as pharmas, universities, research institutes, and they provide a way for these institutes or organizations to access data to conduct research. They are strategic, very strategic, because they help the industry overall and form as an accelerator for research. Yet, they still face very common challenges. So let's talk a bit about that. Because sequencing has become a lot more prevalent and cheaper, we're just generally getting a huge increase in genomic data. And this rapid growth is really in petabytes of data. And that means when you're actually needing to share that data among other organizations, you're talking about an exabyte level of sharing. This large growth of data, together with the complexity of having to analyze a lot of this data, requires a new scale of compute and storage. And when we're talking new scale, we're not talking a few hundred or thousands VMs. Like in many cases that we've seen, you'd need something like 100,000 cores to be able to do one process of, from a result of a sequencing activity. Most organizations don't have that scale or resource. And in many cases, they need to be able to do it in a bursty way, such that they suddenly receive a large data dump and they need to process it in a very short period of time. What's happening because of this is that technology is actually becoming the limiter of research because many organizations are not set up to be able to handle this level of compute. So, how does cloud actually help solve this problem? Well, if you start by looking at the traditional way in which things worked, and when we say traditional, we mean this is how biobanks, research institutes, and pharmas are set up to work today. This is the environment and process that they have when the volumes of data are small and the requirements were actually quite different. And how that works is that all the data is centralized and in a repository. And whenever any researcher or organization wants to conduct research on that data, they basically make a copy and use it on their own workstation or compute cluster, where effectively data sharing meant data copying. So if you think about it, how is this practical when you have petabytes of data? How do you actually manage to process all that data if you're talking about petabytes of data? This requires considerable compute, and many of these organizations have what effectively is fixed compute, and they own the hardware, and they don't have the ability to scale to 100,000 cores to be able to process that data. And with many scientists, they would have to wait in a queue because a specific organization would only have one compute cluster. And for different scientists to be able to conduct work, they have to wait until the other ones are done. And another challenge that this actually poses is security implementation. Because the way that data is shared, each time it's shared in a different way and copied, that means you need to put a specific custom security control mechanism for each activity, for each sharing of data. And that actually makes it quite vulnerable because you don't have a comprehensive overarching security methodology. So, how does public cloud actually change this model? Well, in public cloud, all the data and the compute would be centralized, and the researchers and the institutions would go to that data and compute. So there would only be one copy of the data maintained, and how access to that data would be controlled is using things like IAM and identity access management, where each organization or individual that needs to access that data is controlled. The access is controlled at a very granular level, such that they only access the data they need and only perform the actions they need to for the benefit of the research. And at the same time, because it's cloud based, it provides an elastic level of compute and storage, such that if they suddenly need to do high level processing with 100,000 cores, they have access to that. And it's elastic in the sense that they don't need to preserve that or reserve that compute power beforehand. They use it when they need it, and they only use it while they need it. And this also gives a benefit of having a centralized security implementation, such that the way to control security here is to provide access to individuals or organizations in a very controlled way, and you would have a comprehensive security method implemented. So we talked quite a bit about some of the tooling that's available, and in terms of like what cloud can provide in terms of high level compute and storage and the benefits of that. Next, we're going to be talking about specific tooling that is custom made for genomic data that can be either deployed or natively available on GCP. On to you, Hatem, to talk about that.
Thank you, Hussein. There are many tools that are available to bioinformaticians trying to use GCP for genomics analysis. So let's have a look at some of these tools. Hale is one of the common tools that provide powerful data science tools that can be used to interrogate large-scale data. Hale uses Spark in Hadoop, which means it can be deployed on top of Dataproc, which is our managed Hadoop service. And Hale actually has native support for Dataproc, and we will see more of this later. Pipelines on top of workflow management engines are also among the common tools many bioinformaticians use. We have built the Life Sciences API to make it easy for these workflow engines to integrate with Google Cloud and be able to run at cloud scale. Some examples of the workflow engines that take advantage of the Life Sciences API are Cromwell, which is developed by the Broad Institute. Nextflow and SnakeMake are two other workflow engines that are open source and are very popular in the community. These workflow engines are commonly used by biobanks and research organizations to process and analyze thousands of whole genome sequences with ease. But working with common file formats for genomics and variant data can be challenging when working with machine learning frameworks, which was one of the drivers of developing the Variance Transform tool. The Variant Transform tool is an open source tool developed by Google Cloud and now has many contributors from the community. It can export variance data to BigQuery. This makes it easy to interrogate the data using SQL statements in a very fast and efficient way. It also makes it quite easy to build datasets that can be consumed easily by machine learning frameworks or our AI platform to build new machine learning models. But sometimes, all the researchers want is to simply access raw compute power. It could be that they need a machine with more than 100 cores or even terabytes of memory to run something like a de novo gene assembly, or use an HPC cluster such as Slurm or any number of the tools that they can run on top of Google Compute Engine, such as Galaxy or Toil, which can actually use the Compute Engine APIs to provision instances. Many of the bioinformaticians may also be using research and analysis platform, such as Terra, which was developed by Verily, which is an Alphabet company, also by the Broad Institute, to enable researchers to collaborate on workspaces, share notebooks, and easily launch pipelines through Cromwell integrations. This makes such analysis platforms a one-stop shop to access datasets and be able to run your analysis and share that and collaborate with others. And of course, there are many more tools from the community and our partner ecosystems that can be added to this toolbox for bioinformaticians. So let us look at Hale in a more bit of details. As I mentioned before, Hale runs on top of Dataproc. And Dataproc enables you not just to create a Hadoop cluster in seconds, but also enables you to easily scale up and down this cluster. This flexibility is one of the key advantages of running Hale on Google Cloud. You can easily create a small cluster with just a couple of worker nodes to configure, debug, and test your code. And once you are ready to run your large GWAS analysis or large variant calling analysis, you can easily scale up to hundreds or even thousands of nodes, and you can also add preemptible instances, which can help speed up execution and keep the costs down. Once you're done, you can scale down or simply delete the cluster, as it only takes you a couple of minutes to provision really a new one. There is no more waiting in a queue for the local cluster or being limited by the on-prem capacity. The Dataproc integration is now part of the core Hale library. You can create a Hale cluster from the Cloud Shell in just a couple of minutes with just these two lines you see on the screen. It is insanely easy. If you have attempted to deploy a Hadoop or Spark cluster before and configure and install software and its workers, you would know that it can take days and you may still not be able to achieve the performance and scale you would get from running on cloud. Many of the existing tools use common genomics format, such as FASTQ, BAMs, CRAMs, VCFs, etc. But building datasets out of these file formats or cross-examining with other data coming from healthcare systems, imaging, or even geo or weather data can be really challenging. The variance transform is an open source tool that uses data flow to export your variant data to BigQuery on a standard schema. The use of data flow allows you to scale if you have a large data set, as this could otherwise be a very time consuming process. BigQuery requires zero management and allows you to store and query petabytes of data in minutes, sometimes even seconds, without the hassle of managing any infrastructure and only paying for the queries you execute. There is already lots of public genomics datasets that you can explore today on BigQuery, such as the 1000 genome, platinum genomes, or the public access portion of the TCGA. There is also multiple non-human variant data, such as the Genomics cannabis or the Rice3K, which has variants that were called using deep variants. The other key advantage to having the data in BigQuery is how easy it is to create cohorts and data sets that can be used in TensorFlow or other machine learning frameworks easily. And, and you can take advantage of the AI platform tools, such as the AI notebooks, to interact with your variant data using Python or R very easily. So, Color is one of our customers who did just that. There is a very interesting blog post on our website on how they used variance transform and BigQuery to create machine learning models that beat standard industry models in just weeks. So, one of the reasons many have chosen Google Cloud for the genomics workload is that we don't just provide infrastructure. Our product and engineering teams have developed a number of services and APIs that cater to the needs of healthcare and life sciences community, such as the healthcare API that supports health records in FHIR and HL7 format, or the imaging API to interact with DICOM. The life sciences API was developed to enable workflow engines to take advantage of Google Cloud in large scale. This is a reference architecture for running workflows at scale in GCP. Raw data from sequencers or other sources typically would be uploaded to Google Cloud Storage, and the workflow engine would run on a Google Compute Engine or on your own infrastructure or machine, and then would make REST calls to the Life Sciences API. The Life Sciences API takes care of the full life cycle of each step in the pipeline, from creating a virtual machine with exactly the number of cores and memory specified, localizing the input files and copying them from storage, pulling Docker images and running that step, then delocalizing the output again to the cloud storage. And it is able to do that in scale. The Broad Institute, for example, have used the API to call variants for all 79,000 whole genome sequences in the Nomad dataset in just 3 days. Several workflow engines or batch job managers like DSub take advantage of the Life Sciences API. This includes Cromwell, as we said before, which was developed by the Broad, Nextflow, which we will see later in the demo, and SnakeMake, which is a recent addition. All these workflow engines have very active user community and with many standard and sample pipelines on GitHub that you can easily run. The Life Sciences API makes it easy for the developers of these workflow engines to build quickly on top of Google Cloud and also include tools that allows you to debug your pipeline or generate data that can be used to analyze your pipeline, calculate the compute costs of a pipeline or a particular step in the pipeline. On the right-hand side, this is what a typical pipeline might look like. It's really a series of tasks that may include scattering across multiple processes or gathering and collating them. For each step, the API will create a virtual machine. Once the step is completed, the virtual machine is deleted. This helps keep the cost of the pipeline down, as you don't have to pay for a cluster and standing all the time, and you don't have to pay for any idle instances. Now let us run a sample pipeline on Google Cloud using Nextflow. This is a sample configuration for a profile to run with Google Life Sciences Executor. You'll notice I have specified the region I want my compute instances to be and the bucket used for temporary and intermediate files. I have also selected which region the Life Sciences API will store the metadata about the execution of the pipeline. And finally, I set the use private addresses to true, as I already have an ad gateway set up in the project and I don't want to use public IPs for added security. Now, let's switch to my virtual machine. So now I'm going to run a test pipeline I wrote on my virtual machine. To install and run Nextflow, I need to set some environmental variables I've already done that in my bash RC to save time every time I'm using this. So as you can see, I've added the key to my service account, the version I want to run, and Google as an execution mode. So now I'm going to run the pipeline. I'm going to pass in a config file, which has all my configurations and project information. And I'm going to run my test pipeline, which just compares the performance of GPU versus CPU. I'm going to select the Google Life Sciences profile. And I'm going to add some options to actually be able to debug and monitor the performance of my pipeline. So as you can see, the pipeline is now running. It will automatically create a virtual machine on Google Cloud. To see that on Tower, I can see that now my workflow is running. I can check on the resources and the virtual machine that it's using, and I can actually monitor the while it's being executed. Spoiler alert, the GPU beats the CPU in this one. I can also check previous pipelines that I've ran before. With Tower, I can check the CPU usage, so I can actually optimize my pipeline and select the correct virtual machine shape. I can check memory, execution time, and so on. It's actually very helpful when troubleshooting and actually optimizing your pipelines for cloud. So that was our demo. I hope you enjoyed it as much as I did. Thank you very much for your time. Of course, there are many more tools out there that are from our partners and ecosystems. And if you have any questions, please share them with us on the Dory.
Thank you, everyone, for the opportunity to present to you today. It was very exciting for us. We look forward to seeing your questions on the Dory. Thank you.